Hi, hello guys. It's Tekiso once more. Hell, it has been a very busy last 2 months. But hey, remember, whatever I do, normally I don't forget you guys, man. Hey, sorry to come so late, but I'm here. Let's do problems. I know the exams are here. Some of you, the college guys, are done. I'm told that it's already reopening tomorrow. The classes are starting for trimester 2. That's great stuff. Just put in the comment there if you want me to treat some few stuff. But I've seen in the comment, man, I've been requested to deal with the efficiencies of transformers and induction motors, and the guys say they are writing the exams and he've got some real confusion in it. So yes, today we're gonna deal with induction motors, and hopefully maybe a day after tomorrow we'll release another video on efficiency of transformers and so on. But before we deal with the efficiency of induction motors, let's first look at the power stages that exist in an induction motor. The power stages, because that's very crucial. Basically, this is the diagram. This is the power stage diagram. This is the input power from the galvanic stand, maybe supplying a load. And then this power from the galvanic stand arrived at what is so called the stator of an induction motor. It is the stationary part of induction motors, and remember it has conductors and so on. And then this stator, it consists of the stator copper losses as well as the iron losses. The stator copper losses and the iron losses. And these iron losses are regarded as constant, but you're gonna see why they are regarded as constant. And then from the stator, there should be a power that has to go through what is so called the air gap, and we called that power the synchronous power. And the formula for that synchronous power, it is omega 2 pi ns omega multiplied by the torque or gross torque. Now, as this synchronous power passes through to the rotor, we've got losses as well. This is the rotor, and there are losses as well happening there. We've got the stator copper losses and the iron losses, which are constant. They are constant throughout. So here we're gonna have the rotor copper losses and the iron losses again. And then of course the output of the rotor, it has to be converted into the mechanical energy so that now the motor should start working, and we call that mechanical power. And the formula for mechanical power is equal to what? Is equal to the synchronous power minus the rotor copper losses. Why? This is very crucial. Since the iron losses are regarded as constant, they are normally ignored. And when they are ignored, the rotor copper losses is equal to the synchronous power multiplied by the slip. Now, if there are if the rotor copper losses is equals to the synchronous power multiplied by the slip, we can further deduce this by saying, this is now mass, guys. This is now mass. By saying what? By saying the synchronous power minus the rotor copper losses. But what is the rotor copper losses? The rotor copper losses is the synchronous power multiplied by slip. So on the behalf of this, I'm gonna put this. It's gonna be the synchronous power multiplied by slip. Then of course I can take out a common factor. We discussed this not so long time ago. It's gonna be synchronous power 1 multiplied by S, which is the slip. This is another formula. This is another formula we're gonna use. We can further deduce this as well. From here, we can also say the synchronous power is equals to the rotor copper losses over the slip. And then, okay, for now, let's leave it there. For now, let's leave it there. And then here, this is the shaft output. Okay, let me write shaft. This is the shaft output. And the shaft output consists of the rotational losses. And the rotational losses are of the winding losses and the frictional losses. These winding losses and frictional losses are actually due to the fan at the back of the motor mounted on the back of the motor, and they are mounted on the rotor. So as that fan rotates, the losses that prevails there is this. And then of course at the end we're gonna have the output power, which is 2 pi nr. We call this omega multiplied by the torque. And then what else you think we can do here? We can further say yeah, but that's fine. Basically these are the formulas you have to use to calculate. Remember the input here is equals to the output plus losses. The reason why you have to know the formula for the losses, because you have to add them to the output in order to get the input. That's why you have to calculate this basically. So yeah, this is actually the case. So let's take problems now to calculate the efficiency of the motor. One other thing, guys, I think, okay, one other thing again, let's say mechanical power is equals to, you see here is PS, and PS is equals to the rotor copper losses over slip minus PCUR, the rotor copper losses. I can take the rotor copper losses as a common factor, then I'm left as 1 over S minus 1. So this is the rotor copper losses over the LCM here is S. So I'm going to have 1 minus S all over S. This is another formula to calculate mechanical power. If you know this, these are the basics. You must be able, at least 90% of the time, you must be able to attack a problem. Let's take an example. I don't have space, guys, so for that reason I'm gonna delete here. Yes, let me delete this. Do yourself a favor, man. Try this at home. Try this at home. Too often. And you'll see with time, they become easy. They become easy. One other thing. This is engineering. This is engineering. You do induction motors. You do this example. Go ask anyone to show you what is an induction motor. There are people at the university who just study and they have never seen a motor before. Just go ask them this, where is the stator? No, it's this one. Where is the rotor? After that, relate what you have seen to this. You'll see it becomes easy and it becomes routine. Let's take example from Taraja. Example from Taraja. It says 100 kilowatt. That's another cache. That's another cache, and that's when normally people make a mistake. If a statement starts by saying 100 kilowatts, then you must know it's an input. It's an input. It's an output rather. Sorry. If they want to give you an input, they will tell you an input to the motor, then you know it's an input. But if it says 100 kilowatts, 3,300 kilovolts, 50 hertz, three-phase star-connected transformer, it is the output. This is the information on the nameplate of that particular induction motor, and it's an output. These are the rated values of that particular motors. That motor. Right. Now, 100 kilowatts. This is an output. 300 volts, 50 hertz. This is the standard frequency of South Africa, 50 hertz. Three-phase star-connected motor. You saw this during the process when we were dealing with transformers. Star-connected induction motor. Induction motor has a synchronous speed. NS. This is an abbreviation for a synchronous speed. If it was R, it would have been the rotor speed. It has a synchronous speed of 500 revs per minute. And the full load, this is the full load slip. The full load slip, or let me put it this, a slip at full load is equal to 1.8%. And it has a power factor of 0.85. This 0.85, it is actually the standard power factor of South Africa. 0.8 to 0.5. That's the standard power factor. And you are also given the stator copper losses, PCUS, copper stator loss. The stator copper losses is equal to what? Is equal to 2440 watts. The iron loss, the constant iron loss is equal to what? It's equal to 3,500 watts. And we've got what? Rotational losses like this, plus F. Rotational losses of, these are rotational due to the fan. These are the losses due to the fan. It's equal to 1,200 watts. Now, calculate the rotor copper losses, the line current, the full load efficiency. Now, Now, gentlemen, it's simple. Look. Always, that's where you should start. This. Your power diagram. And you've got the input, which is, of course, the output plus losses. You already got the output there is given as 100. You are yet to find losses. Let's come here. You are given the stator copper losses as 2440, and then the iron losses as 3500. Hey, sure, guys. Sorry, man. Maybe in the long run you're gonna see as if the video is cutting here and there. There are people sitting here as well, and they are given a chance maybe to do a problem, and then when we do corrections, it's only now then that I continue. So I hope maybe you will forgive me for that. I really apologize, but I hope you don't see such. So yeah, these are the stator copper losses, and they are given as so much, 2440 watts. Let me put watts. This is very, very important. Units, it's watts, otherwise you are out. And then here you've got the synchronous power. This synchronous power is equal to 2 pi stator speed multiplied by the torque. And then, of course, here we've got the rotor with, of course, rotor copper losses. And then the iron losses, which are constant. It means here as well, the iron losses is 3500. And then here, we've got mechanical power. I'm just doing it in detail so that maybe when you do problems, fill this program, fill this sketch incomplete, and then from there you answer questions already with answers here. You just take answers here because you have calculated them. This mechanical power is equal to what? Is equal to the synchronous power minus the rotor copper losses. Minus the rotor copper losses. And then here we've got the winding losses and frictional losses, and they are given as how much? 1200 watts. And of course here we've got the output, which is given as 100 kilowatts. 100 kilowatts. Now, very important. If you go up on this sketch, you add the losses. But if you go down with regard to this sketch, you subtract from the input power. Now, let's check. If you add the output power to this winding losses, you must get that. And you have to see to it that the units are the same. It's kilowatts, it's 1200 watts. So you can convert either this or that. Let's convert this one, which is 1,2 kilowatts. How do I know? You divide by 1,000. It means 1, 2, 3, which is 1.2 kilowatts. Now, 100 kilowatts plus 1.2 kilowatts is equal to what? Is equal to what? Pmax is equal to 100 kilowatts plus 1.2 kilowatts, and it's equal to 101,2 kilowatts. You got the mechanical power there. Now, you are also given a slip of 1.8. A slip of 1.8. Let's see. let's calculate let's calculate let's calculate the synchronous power first. Synchronous power. Let's look what's going on here. Let's calculate. We calculated the mechanical power. We got that. Now, what's going on here? We will say the rotor copper losses is equal to the synchronous power multiplied by slip. But we don't have power. It means the mechanical power as well is equal to the rotor copper losses into 1 minus the slip over S. We proved this formula before. We've got this, we can find that. And it's equal to what? Let's say it's 101,2 is equals to the rotor copper losses into 1 minus what? 1,8 divided by 100 is equal to what? 1.8 divided by 100 is equal to 0,018. 0,018 over 0,018. So it's 1 minus 0.018 divided by 0.018 is equal to what? 54 is equal to 54.56. 54.56. Okay. Take this. Just do this. Let's say P C U R is equals to 101,2 divided by 54.56, and it's equals to what? 101.2 divided by 54.56 is equals to 1,855 kilowatts. Gentlemen, I hope you see. Just follow the video, watch it completely from the end to the start. But this should make sense. Especially the main point is this. You know, this is that. I've substituted the slip there. I've got the mechanical power. I've just made PCUR subject of the formula. To calculate it, I got 1,855. Basically, this is the answer, but you are not yet there. You were requested to calculate the rotor copper losses, and from your sketch, you found them as 1,855. Right, now you've got this, and this. You can also find this. I want us to fill in our sketch first. Now, PCUR, the rotor copper losses, is equal to what? PS, synchronous power, multiplied by the slip. We just make the synchronous power subject of the formula. This is calculated as 1,855, I think. Yes, divide by 0,018, and it's equals to what? It's equals to 1,855 divided by 0.018, and it's equals to what? It's equals to 103,06 kilowatts. You've got the synchronous power there. Now, very, very important. The question now arises, what is the input power? It is the output plus losses. The output is given as what? It's given as 100. I can bet with you, the reason why people struggle with this, they consider this 100 kilowatts as an input power. That's not. You have to calculate the losses first and add them to the output to get the input. That's why most of the time people get this very wrong. Right, this is 100 plus losses. What are the losses? The losses is 1.2 plus what? Plus 3.5 plus what? Plus 2,44. These are the losses. 1 losses, 2 losses, 3 losses. And it's equals to what? It's equals to 100 plus 1,2 plus 3,5 plus 2,44 is equals to, am I missing something? Am I? Yes, you are. You are missing the rotocopper losses. We are missing the rotocopper losses plus 1,855. We are missing the rotocopper losses. So now we've got 1, 2, 3. But these ones are constant. That's why you only take it as 1. Now you have to get what? 100 plus 1,2 plus 1,855 plus 3,5 plus 2,44 is equals to 109. 109 kilowatts. 109 is 108,9999. It's 109 kilowatts. Now you have filled in the sketches. This is the advice I will give. Now the question is calculate the rotocopper losses. Straightforward. We have already done that. The rotocopper losses, and they were found to be as 1,855. Straightforward. The rotocopper losses PCUR is equals to 1,855. Why? You already calculated them from your sketch. Right. And then the line current. The line current is equals to what? Power is equals to root 3 V line I line cos of phi. I line is equals to the input is 109 multiplied by 10 to the power 3 over square root 3 multiplied by the voltage is given as 3,300 multiplied by the power factor is given as 0.85 and it's equals to what? It's equals to 109 exponent 3 divided by second function square root 3 multiplied by 3,300 multiplied by 0.85 closing the brackets, and it's equals to 22,44 amps. This is the line current. And then they say calculate the full load efficiency. The efficiency at full load is equals to what? Is equals to the output power over the input power multiplied by 100%. Why? To express it as a percentage. That's why. And it's equals to what? It's equals to 100 kilowatts, which is given over 109. That is calculated and found to be 109 multiplied by 100%. And it's equals to what? It's equals to 100 divided by 109 multiplied by 100%. And this is 91.7 And basically this is 15 marks. Guys, please give yourself a chance, put some effort. Even if you are working, do one problem every day. Make sure you understand the sketch. Make sure before you answer, you know how to fill in this diagram. With time and patience, there will be a clearer picture. I will see you in the next video, possibly with a continuation of this. Bye bye.